Welcome back. This is Unit 7, Day 3, and we are covering Section 7.2 in the book that I don't use anymore because I make copies of the homework. But, whatevs. Okay, we are going to be talking about areas in the plane. Okay, I like this, and I like when it goes to volume and eventually discs and washers, but hold your horses, we'll get there eventually. The Gateway Arch in St. Louis, Missouri, an appropriate photo for what we're about to do because, wow, look at that area on the plane. Bang, bang, be nice to get all this area, wouldn't it? That's what an integration does for us, children. Let's begin. Oh, homework answers. You're welcome. All right, now, how can we find the area between these two curves? All right, we know how to find the area under one curve. That is simple integration, all right, an integral. So how can we find the area between two curves? Well, it probably has to do with an integral again. We're going to have to do integration. But let's think about this. If I wanted to do the area just under this arch, like right here, I would just go, and I'll do this in green. Let's do highlighter. Man, can't believe I almost didn't use the highlighter. I would just do the area here, and it would be the integral, right? The integral, because an integral is the area under the curve actually to the x-axis. So, but I'm not doing that, am I? I'm doing the area not only under this curve, but between that curve and this straight line, okay? Which a straight line we're calling y2, and that function is negative x. And the curve, in case you couldn't tell, is y1, and that is 2 minus x squared. So now here's the thing. I don't want the area just to the x-axis, but I also want to include this as well. All right? So I'm going to do the area, the vertical sort of shapes between all of this. Okay? I want all that area. Okay? So this next thing says consider a very thin vertical strip, which is what I just, illustrated for you here. I'm kind of going ahead of myself. It says click the graph. Let's see. I can't forget. Boom. Oh, there it is. Look at. I want to add up all of those vertical lines, the infinite amount of vertical lines that I could put in between those two functions, in between those two graphs, the curve and my straight line. So if the length of a strip is, okay, we need to figure out how can I calculate that strip. See you later, Mr. Plane. I just take my upper graph and subtract my lower graph. Let's think about that for a moment. Whatever value this is, let's say that's at 5. And whatever value this is, let's call that, I don't know, -2. If I want to find that distance, I take my upper one and subtract my lower one. That would be 7. This would have a distance of 7. That works at any 2 points that are above and below each other on these two graphs. You just simply subtract them, okay? But the thing is, I don't necessarily have a 5, and I don't necessarily have, a -2. So how do I figure out what those y values are? I don't know what the y values are, but I know how I could get the y values, okay? My upper graph, whatever this is, I plug an x value into 2 minus x squared. Okay, whatever this is, I plug an x value into -x. Okay, so I still subtract them. This is my upper curve or graph, and this is the one below it. Remember, in subtraction, order matters. Okay, in addition and multiplication, it does not. But in subtraction, order matters. So we always want to make sure, you can visualize what the graph looks like. And the higher one, okay, the greater one, the one that is on top, should always be the first in the subtraction. And you subtract the one that is on the bottom, okay? Always, always, always. Now, let's move this over here. What am I to do? Now, what about the width? We just figured out the length. We just figured out this length. All we do is, in our case, we take y1 and subtract y2, right? But what about this little small change? The actual, that's not an h, that's kind of like a width bar of my green line here. A very small change in x, because remember, this is the x-axis. It's changing very small from this side to this side, right? Let's not forget in calculus, we represent that very, very, very small change in x. Okay, wait, here it goes. Whoosh. See ya. Enjoy Hawaii. Anyways, we call that dx. So if I want to figure out the area of that bar, length times width. Length times width. Can you see where we're going with this? And once again, I have logically went where the notes should go. Length times width is right in front of our face now. Since the strip is a long, thin rectangle, the area of the strip is length times width, which means I hope they're going to Aruba. Anyways, I take my length and I multiply it times my width. Now you might be saying, whoa, Visca, whoa. I thought you were supposed to subtract the bottom. Well, let's not get crazy. If we have 2 minus x squared minus a negative x, don't forget when we subtract a negative, it turns into a super positive. That's what they tell my sonnies in middle school. It's a super plus. And I like saying that now. It's weird, but I do. Anyways, that is the area of 1 right here. This right here is the area of this one strip. But let's not forget, we want to add up all of them because we want the area. Oh, highlighter opportunity. We want the area of all this stuff right here. We don't want just the area of that one, which means I want to add this strip to this strip to this strip to this strip to this strip. And then we have an infinite amount of strips, okay? And I know here too, I know that's more of a sine curve that had a stroke, but play with me. You know they should be straight lines. Okay, remember, we add up all those strips. What did LRAM turn into? Integration. We are going to integrate this. All right, we're going to integrate this. But here's the catch. Let me explain one thing to you about our integral. And it's really not a catch. It's just common basic math. Okay, length times width. Okay, I integrate it because I add them all up, but where did my upper and lower bounds come from? Okay, sometimes in a problem, okay, 2, this is where they meet, and -1 is my lower bound. In a problem, sometimes they'll just give those to you. They just gave them to you right here. But if they didn't give them to us, how can I figure out these 2 points? Well, where does my upper graph, okay, meet my lower graph? So I want to find the intersection points between 2 lines, okay? I want to see where they intersect here and intersect here. That is basic algebra. Algebra 1, definitely algebra 2, okay? When I have 2 graphs and I want to know where they cross, I set them equal to each other and solve. Okay? If I had a graphing calculator, if this was a problem in the final and they allowed a graphing calculator, I hope you would graph it and then use your second calc, okay, and use the intersection button. What do I mean? I mean, if I open up this thing, I hit second and trace, okay, and that above there is blue. It's the calc menu. And you can figure out the intersection of where these graphs meet. You can do that. But if this was not a question where you would get a calculator, you simply take your equations and you set them equal and you solve. I'm going to bring everything on the left side over to the right. So I'm going to subtract 2 and add x squared to both sides. We're just going to do this really, really quickly. So I've got 0 equals, I have a positive x squared, a minus x, and a minus 2. Factoring never goes away, okay? I teach 10th, 11th, and 12th graders. I think I need to go down to 6th, 7th, and 8th grade and tell them that factoring never goes away, all right? So x minus 2 times x plus 1 equals 0. That's what I call a booty cheek, and now I T-bone it. My x equals 2, and my x equals negative 1. Oh, what a coincidence. 2 and negative 1, which is right here. Okay? So we're good. So that's where those intersect, and that means that's where I'm going to have this section. Okay? This is where I'm going to have this section to find the area in between. And I've spent a lot of time talking about basic math stuff. Let's start doing calculus stuff again. Okay? Let's start doing calculus stuff again. All right, so the next slide gives us a little bit more room. It gives us our integral. And now we're actually going to solve this area between the curves here. Okay? Now I'm going to basically just integrate this. This is not an indefinite integral. I'm not going to have plus c because I have my bounds. This is a definite integral. So I integrate 2, and I get 2x minus. I integrate x squared, I get x cubed over 3. Okay. Plus, I integrate x, and I get x squared over 2. I want this from 2 to negative 1. So let's be careful and not make mistakes, and let's put the 2 in first. Okay? So it's 2 times 2, I'm putting it in for x, minus 2 cubed, putting it in for x, over 3, plus, putting it in for x, 2 squared over 2. This is my first term. All right, now we need to subtract, putting in the second term. Okay, so minus, I put a negative 1 in here. 2 times negative 1 minus negative 1 cubed over 3 plus negative 1 squared over 2. All right, so this is my second input. It's my lower bound. So I take the first and I subtract the second. All right, just be very conscious of the minus signs and the negatives, and do everything you need to do. This is 4 minus 8/3. Okay, that's 4 over 2, which is 2. If I simplify that, I get 4 and 2 is 6 minus 8/3. 8/3 is the same as saying 2 and 2/3. So if I take 6 and subtract 2 and 2/3, I will get 3 and 1/3, which we would lovingly say is the same thing as 10/3. This is just this side. I still need to subtract my other side, okay? Okay, I get negative 2 here when I multiply this. I subtract a negative 1/3. So you got to be careful with that stuff. Plus a half. Let's do this. I've got negative 2 plus a third plus a half. Okay, well, let's make this a common denominator and combine everything here. 6, so I got negative 12 over 6, that's negative 2, plus 2/6, that's a third, plus 3/6. And when everything is all said and done, that is negative 10, negative 7/6. And I have 10/3, but I am subtracting, okay? Here is my left parenthesis I started with. Here is my right parenthesis. So ultimately, when I subtract a negative, okay, I am going to add, all right, add 7/6. So I've got 10, well, let's convert this to 6 as well. 10 over 3 is the same thing as saying 20 over 6. So multiply both the top and bottom by 2. Plus 7/6. That's 27/6. I could reduce that if I want to. 3 goes into both of those. 9/2. area under the curve. That is a lot of algebraic work, and that's fine. This is the type of problem, I get the sense they would not give you a calculator with this one because your denominators are 2 and 3, and you're not working with like 51 or 117. And it's not getting crazy. This is simple algebra you should be able to do, especially if you're in calculus. Stop it now. Don't look at me and say, really, Visca? Yes, really, you're in calculus. So, in conclusion, or in summary, the formula for the area between curves is, oh, hopefully that's Jamaica. Anyways, I take my two functions and I subtract them, okay? Here's my upper bound, my lower bound, whatever it might be. I just subtract my two functions, dx, that's it. But remember, Punta Cana, I hope that's the Dominican Republic. The top curve minus the bottom curve, okay? You always want the curve on top on the graph to be first and subtract the bottom curve or the lower curve on the graph second, all right? So what about this, Visca? There's someone that always asks me this. What about this, Visca? Because look it, I want to take f of x in the top and subtract g of x, but I can't do that because on the right side, okay, g of x is on the top, all right, and f of x is on the bottom. Interesting. This was drawn, this is part of the notes. I didn't draw this and not show you me drawing this. This was here, okay? It's my handy craftsman and my artwork, right? So how do I do this? Okay, you ready? Are you ready? Okay, so I need to find the area between the curves. So first, I'm going to find the area here. Okay, that's the integral from 0 to -5 of my top curve minus my bottom curve. Okay, and I want to add that because I want the area between all the curves. I'm going to add it to this area. So how do I do this area? Well, I do it like it's a separate integral plus the integration from 5 to 0. But now it's g of x because g of x is on top minus f of x dx. Okay, I can break that up. There's no rule saying I can't break that up. If I had 13, can I break that up and say that's 7 plus 6? Sure enough, I can. And that's exactly what I would do with integrals in this case. All right? So there is always an answer. Sometimes the answer is I don't know, but in this case, I do know, and now you know. Let's proceed. All right, let's look at example 1. Find the area between the functions y equals x minus 2 and y equals the square root of x from 0 to 4. They give us bounds, okay? And I have a picture right here, and I love it. I love it. So this is what I'm going to do here, okay? I kind of have a special shape, and let me explain something to you right now about the way this kind of looks, all right? Here is the square root of x. Here, I won't do this in blue because everything else is blue, is x minus 2. Okay? I can do the area between the curves because I have area between the curves here and here and here. However, I do not have my y minus 2 does not go here. Okay? So this area here is not between the curves. The area that I've highlighted in blue is between radical x, okay? It's between radical x here and the x-axis. That is just a basic integral, okay? So how am I going to do that? I'm actually going to divide this up right at 2. Okay? I'm going to divide that up. So how am I going to do this? In order to find the blue area, I'm simply going to take the integral of the square root of x. that there gives me the integral between the square root of x and the x-axis. Okay, technically, okay, what is the x-axis? Doesn't that have an equation of y equals 0? I mean, it does. I mean, I could put, if I wanted to, I could put minus 0 here, but then this just goes away. So that's why all of our integrals, when we don't have two functions, all of our integrals are just the one function to the x-axis. Okay? We don't need anything else. And I want that from 2 to 0. Yep, I'm a step ahead because I'm going to add 2 to 0. Now, I add the integration from 4 to 2 of, okay, the area between the lines. Top function, which is the square root of x, minus the bottom function. Please, you are subtracting everything. If I did not have these parentheses here, that would be wrong because I'm just subtracting the x. I want to subtract the whole second function. Parentheses are important. Now, you can integrate this, and for the sake of time, we're gonna do this in our calculator. But if you're gonna integrate this, you should make that x to the 1/2, and then you add 1 and divide by that, so it'd be 2/3 x to the 3/2. And you have the same thing here. Okay, then you have to put in a 4 and a 2 and a 2, and it'll get a little detailed, and we can do it. But again, for the sake of time, let's actually do an integral in the calculator because we don't do that often. Okay, let's do this in the calculator. So on, let's quit. That is on. I'm going to hit math, and is it 9? The integration it is. So I'm going to do this first one from 0 to 2. The square root of x dx. First one's done. Plus the integration from 2 to 4 of the square root of x, pop out of that radical sign, minus parenthesis x minus 2 parenthesis dx. And when I hit enter, let's see if it's anywhere in the ballpark. All right. Now, if I wanted a fraction, I hit math, enter, enter. It won't, because you see that 544 at the end? The answer to this, okay, the answer to this is actually, and I've done this on paper, and it's really not horrible, 10/3, which is 3.3 with a line over it. Keep in mind, and I'm glad we did this in the calculator, anytime you do something in the calculator, it could be off by a smidgen. Technically, let's do this in black. It's off by tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millionths. It is off by 3 10 millionths, which is not that difficult, but it is not exact with your answer either. If this was multiple choice, I hope you would realize, this is what you need because it's equal to this. But if it's not, I mean, hopefully they tell you to round to the nearest 100,000ths. If they ask you for an exact answer, I hope you have enough common sense to change that to 10/3, or you would have to do this out, which again is not horrible. I just wanted to save some time. Now, example 2, find the area between the two functions, y equals x minus 2 and y equals radical x from the same bounds. We should get the same answer. This was our answer, but we're doing this horizontally. Notice, okay, notice my functions are left to right when I'm doing this horizontally. So instead of up and down, I go left and right. Which is the bigger function? This is further right. This x minus 2 is further from my y-axis than this is, okay? All right, so my top function is x minus 2. My bottom function is the square root of x. Now, why would we possibly do it this way? Because we can do one integration, meaning I don't have to break it up into two. Every spot, if I'm doing horizontally, is exactly between these two curves. Okay, my previous one, was between the two curves. That's why we came up with this. But then this wasn't between two curves. So I kind of had to do a second integration on its own. All right? This one, I don't have to do that. However, you need to be very careful. How come? My bounds are no longer on the x-axis because I'm doing this horizontally. This goes from 2 to 0. Okay, I'm going from 0 to 2 because it's the x-axis. All right? So if my bounds are y's, that means my variables in my equations should be y's. So these should be x equals. I'm going to have to convert both of those to x equals. If I have y's in my bounds, I should have y's in my integrand. Okay, they should match. So let's quickly convert these. The first one's easy. If y equals x minus 2, I'm just going to add 2 to both sides. So I get y plus 2 equals x. Okay, this is in terms of y of my bigger function. All right. Now I've got to subtract my smaller function, right? So let's convert my smaller function. Y equals square root of x. How do I get this in terms of y? How do I make it x equals? Well, I'll just square both sides. So x equals y squared. That's my lower function, okay? That is a million times easier to integrate. I'm going to integrate this from 2 to 0. Y becomes, y becomes y squared over 2, okay, plus 2 becomes 2y minus y cubed over 3. I want this from 2 to 0. Let's plug in our 2 first. 2 squared over 2 plus 2 times 2 minus 2 cubed over 3. That is just with my 2 in. Minus putting my 0 in. I'm going to humor you. Everything I put a 0 in here is going to go away. 0 squared over 2 plus 2 times 0 minus 0 cubed over 3. 0, 0, 0. I just need to worry about the left side. Okay, 2 squared is 4. 4 over 2 is 2. Plus 2 times 2 is 2. Yeah, 4. I'll be okay. 4. I had too many 2's in the mind. Minus 8 thirds. Ultimately, that's 6 minus 8 thirds. Let's get a common denominator. That is 18 over 3. That's 6 minus 8 over 3. And lo and behold, 10 over 3. This, if I didn't have a calculator, this method was a million times easier to integrate than this one would have been. In fact, now I kind of wish I showed you all the hard work I had to do in the integration process. Here, what made this difficult? This is new, doing it horizontally. If I have, and let me explain to you one more time, if my bounds are y's, okay, if I'm doing horizontal, okay, I'm going from 2 horizontally to 0 on the y-axis. If my bounds, if I'm using y's, I have to have y's in my variables and my integrands. Okay, if I were to use this, that does not have a y in it whatsoever. These equations now need to be x equals y plus 2. This is what I use. This equation has to be x equals y squared. That's what, excuse me, my goodness gracious. That's what I have to use. All right, so let's go over some just last quick general strategies for the area between the two curves before we go. Okay, bam. First, I would definitely sketch. I would sketch the curves. I definitely would. Then I would decide on vertical or horizontal strips. Meaning, would I do the up and down so everything would be x's? Or I do the left and right where everything would be y's. Okay, vertical are your x's in everything. Horizontal means you're putting y's in everything. Okay? So pick whichever is easier to write the formulas for the length of the strip. Okay? And or whichever will let you integrate fewer times. Okay? You don't have to. I just like everything x is Visca, and I would have done it the first way anyways. Good for you. This makes things easier, okay? You write an expression for the area of the strip, which is the integrand. That's what you're going to integrate, okay? If the width is dx, then the length must be in terms of x, okay? If the width is dy, then the length must be in terms of y. Look it. If this is in dy right here, see that? Boom. Then you got to have your y's here, all right? If this width is in dx's for these vertical lines, then all these got to be in x's, okay, in your integrands. I think, quite honestly, it's easier to just think, okay, vertical are your x's, horizontal are your y's. Because 3, that's kind of just reinforcing that. 4, find the limits of the integration. That's your bounds, your upper bound and your lower bound. Okay? Again, if you're using dx's, if you're x's, then your limit should be x values. If you're using dy, then your limit should be y's. Again, horizontally, everything's y's in your integrand and your limits. Okay? If you're doing it vertically, well, then these should all be x's, your integrands and your limits. Okay? It's a simple step. I've reinforced it now. I've set it in 2. I've reinforced it in 3. I've once again reinforced it in step 4. How come? Because people will change the equation without changing the limits, or vice versa. Okay, so make sure you do that. And 5, boom, integrate and find your area. Okay, and again, it's the top function. If I am using dx or whatever, it's the top function minus the bottom. Okay, if I'm doing this horizontally, left and right, okay, and I have something that looks like this, and something that looks like that, the further away from the y-axis you go, this is your upper bound, okay? This is going to be, excuse me, not your upper bound, your bigger function. So it's this one minus this one. That was a lot to do, okay? But you know what? Practice. You practice it, you practice it, you practice it. We've been doing integration for a little bit of time now. You guys have been good with it. So what's the big deal here now? I don't know, you just subtract the 2 equations. That's really it, okay? Sometimes you do it horizontally where you use all your y's. Most of the time, you still do it vertically and use your x's. You still integrate. If you feel comfortable integrating, you feel comfortable doing this. We'll see you in the next lesson.